before I forget. Welcome back. I'm sharing my screen. Okay. I did some, I cheated and I wrote out some review so that we didn't spend half the class writing out the review from last week. So, in terms of what we need from last week, this week, we need to remember the different shapes of distributions. And so when we visualize numerical data, we usually make a histogram, as we saw. But in general, one of the main things that we're looking for are the different shapes, right? And so we will focus on unimodal distributions this week, okay? And for the rest of the term, it's not really going to deal with multimodal. But what does unimodal mean? It means one mode, and a mode is a peak, right? And so each of these examples just has a single peak. But these shapes are all different from each other. This one is unimodal and symmetric, right? And so it's got one peak and it's symmetric about that peak. In fact, it's decreasing down, and so it's a special case, and we call this the normal distribution. It's a normal shape. And then making these two just non-normal unimodal distributions. And there are other options, but these are the ones that we care about, okay? And so here, these would be considered non-normal, but really anything that is just not a normal shape, so not like this first one, is just lumped into a non-normal category. And we ended last day saying, well, the shape of the distribution will determine the best measure of center and spread, which is where we'll pick up today after all this review. But it's important to remember this stuff. Now, we call these skewed distributions, right? These distributions are both skewed, and they're skewed in the direction of the tail, right? And so, and I find that that can be a little counterintuitive, right? Because human nature wants to talk about the lump, right? But in statistics, we want to talk about the tails, right? The tails are those extreme values, kind of more interesting values in terms of analysis. Okay? And so we say this is skewed right. Oops. If I can spell it, skewed right, or a positive skew if you want to talk about positive and negative, but I'll talk about left and right. And which means that this one is skewed to the left, or just skewed left. Two different shapes, but we consider them both non-normal, so they just get lumped into a non-normal category. We also talked about, okay, well, to summarize a distribution, we need to talk about three things, right? We need to talk about the shape, right? Now we have terminology for those shapes that we can apply. We need to talk about the center. Now, when we're looking at a distribution, a histogram, for example, like we did last week, we would say just kind of eyeball the center, right? Where is the peak? Yeah. And for the spread, really what I'm looking for is just a minimum to maximum of possible values. Okay? Because then what we said, what we kind of led into last week is we said, well, we don't worry so much about the center and spread being perfect just by eyeballing it, because we're going to calculate it, right? And so that's why it doesn't need to be bang on, right? It's just to get an idea of what's reasonable. So, and this little tidbit is snagged from last week. But which numerical summary is appropriate depends on the shape of the data, right? So we split it into a normal distribution, right? Special case, but frequently occurring, right? It happens, it's partly why we call it a normal distribution, is because it's really common, right? Kind of as the name implies. If we have a normal distribution, then for the center, for our measure of center, which we calculate, right? Then we use the mean. The mean we saw last week, but we'll talk about it a little bit more in review, is the average, right? And so the average is really only appropriate if you have a normal distribution. If you have a non-normal distribution, which is anything that's not shaped like this, then you should use what's called the median. And so later today, I'll show you how to calculate the median and the standard deviation, which is the measure of spread if you have a normal distribution. And I'll also show you how to find the interquartile range. I know it's long, but it's not that bad if you have a non-normal distribution. Okay. So from last week, your job is to remember, okay, if I have a normal distribution, then I use the mean and the standard deviation as my measures of center and spread, right? And if I have a non-normal distribution, then I need to use the median and the interquartile range as my measures of center and spread. Okay. I had to cave, and I posted the formula sheet on Moodle. Now the formula sheet looks like this. And you know, I'm a little bit wishy-washy. I don't want to overwhelm you. We will pick a way through this nice and slowly, but we do need this section of the formula. Well, we'll work through this section, this entire section, descriptive statistics, because we're describing a distribution, right? We'll work through descriptive statistics today. So that's why I had to cave and post it for you. So it is on Moodle, but I'll bring in sections as we talk about them. In fact, here is the first part of your formula sheet. Now this looks like a lot, and I guess it is. But this is review from last week. I'll still talk about it. This is from last week. Okay. First, we introduce the notation of X bar, right? Anything with a bar over it means that it's the average or the mean. In this case, it's the mean of the X's. Okay? And so in terms of your data set, right, you would have some column X, just generic X, might be GPA, it might be IQ, it might be speeds, right? Any sort of numerical data. Okay? And so, but generically we call it X, right? It's just a placeholder. And then, so this is the column in your spreadsheet, right? If you want to imagine that. And then you have your X subscript 1, X subscript 2, X subscript 3, all the way up to X subscript N. All of these little subscripts just denote that, hey, this is the measurement from observation 1, this is the measurement from observation 2, 3, all the way up to the nth observation, which is your sample size, right? If I gave you a list, like if X was 4, 3, 5, and 9, and I asked you to find the average of these numbers, You know how to do that, right? What would you do? You would add them up. What does that look like? Looks like this, right? Generically, x1 plus x2 plus x3 all the way up till you've reached the end, xn. And then you divide by however many values you have, which is your n, right? So then we introduce this shorthand. If I work backwards a little bit, right? We introduce this summation notation, right? Which is a capital sigma, but it's really just saying, hey, take all your x subscript i's, and you can ignore the subscripts if you want to. If you don't like the subscripts, it's okay. So take all your x is, I guess, and add them all up. You can multiply by 1 over n, but really the only one that I work with is this one here. Okay. The rest is just extra. That's just me giving you everything that you could possibly want, even though it might be overwhelming. All right. So for me, as long as you use this formula, right? Or if you prefer to always use this formula, that's fine too. Okay. But just remember, you know how to find the average of something. Okay. And so here, it's just saying add up all your x's and divide by however many things you had, right? Which is your n. So that means that this section is for today. New today. No? That's a lot. Ugh. I'll come back to this. I want to introduce it first, do it justice. So here we said start here on Tuesday. Well, here we are on Tuesday. Today. I'll call this the end of the review. When I do that little tilde, but sometimes I forget, so hopefully it's obvious once you've reached the end of the review. You'll see why I need to do fresh for the variance and the standard deviation, because they're kind of big. One thing to note is that I've talked about the standard deviation. And one thing that I'll make a note of up here, note the variance is the standard deviation squared. In this course, even though we start by introducing the variance, just because the calculation is just so minorly more simple, we start with the variance, but then for the rest of the course, we only use the standard deviation. But it's really just to introduce the calculation without bogging us down with what? A square root. If it's the square of the standard deviation. Ignore the rest for just a little bit and just focus on this s squared and this s. S squared is the variance, and S is the standard deviation. So if you really kind of dig deep, you'll see that those formulas, the standard deviation is just taking the square root of the formulas above. And so we'll start with this formula here. And then I'll just briefly talk about this other formula, but again, really, you only need the first one. It's just if you like the second one better, you are allowed to use it, and I'm giving it to you. But I tend to only use the first one. Because I find that it's more informative, but they do the same thing. In fact, besides on an assignment, I will make you go through the motions of calculating the standard deviation, okay, but not on a test. Okay, it's just calculator work, right? And so it's good to be able to read a formula like this, right? Be able to look at this and say, yeah, I can tackle that, right? I know how to do that, right? But it's not something I'm going to test you on, right? Just assignments, right? Where you've got time, you can talk to your friends, you can talk to me, you can ask the internet, that kind of thing, right? And so, but not on a test. So we'll start with the variance, but what I wanted to say in this note, but later we will only use, standard deviation. We need to know the link between the two. And I'm noticing an inconsistency in my formula sheet, but I'll keep it to myself. What is it? Okay, I can't keep it to myself. I like using this formula for the variance, but then the corresponding formula is this for the standard deviation, and then I guess they should have lined up better, but room for improvement. Okay, so the variance, what's the variance? Well, variance is going to be a measure of spread, just like the standard deviation is. Okay? And so the variance is a measure of spread. Okay. Now, what it does is, if you ignore the summation, right, for just a second, then what it does is it takes each value of x and subtracts the mean, which means first you have to find the mean, right? And then you're taking each observation in your data set, right, of x, and seeing how far is it from the mean, right? That's the spread, that's a spread, okay? And so that's what we call a deviation. Okay? So first, how far is each value from the mean? Some will be below the mean, some will be above the mean. That's just how the mean works, right? So then if we added them all up, because of how the mean works, they would add to 0 or something kind of useless. But we know there's spread because everything's around the mean. Okay? And so that's the reason we have to square things. Okay? There's more to it than that, but squaring any value makes it positive, right? So if you square a negative, negative 2 squared is 4, right? And so 2 squared is 4. And so if you square something, it makes it positive. Then if we add those all up, all these squared deviations, right? Then divide by n minus 1. And this n minus 1, we're not going to bother with why it's n minus 1, but I will tell you it's not n like you might expect it to be, because n minus 1 gives us a better approximation, okay? And obviously that's a whole can of worms, and it took them a while to get there, because I think intuitively you would want to just divide by n, right? But it turns out n minus 1 gives us a better value, or a closer value to the real deal. And that's how you calculate the variance. So they didn't quite do it in this example, but if we have the hours of sleep per night for 217 people, right, students, whatever, we're told that the mean is 6.71. Notice that 6.71 is at the peak. And so for normal distributions, like we said, this looks like approximately normal, right? The mean is a good measure of center, right? Which we know, right? Because that's why we need a normal distribution to use the mean, right? But it's also because it's roughly at the peak, right? So it ends up roughly at the peak. And so here, the mean is equal to the mode, or at least roughly equal to the mode in a normal distribution. So the variance is going to give us a measure of the spread, not just the minimum to the maximum, but kind of a more elegant measure of spread. By taking each observation, how far is it from the mean, squaring it, adding those all up, dividing by n minus 1. Right? We have 217 lines, right, or rows in our X, and so they don't show it all, but the first observation looks like it's a 5. Right? So 5, so really what this spreadsheet would look like for your X, we're told the first observation is 5, then it's 9, and then we've got a gap all the way up to 7. We don't know what happens in between there, but we know that n is 217. So there's 217 values in there. 214 we don't see. That's okay. Because from here we kind of get the idea, right? So if the mean is 6.71, we can find how far is 5 from 6.71. It's a little bit below 6.71, so it's negative. But then once I square it, I get a positive value. Right? It also amplifies it a little bit. Right? Then we move on to 9. How far is 9 from the mean? 9 minus 6.71, square it. And then we move on and you do that. You wouldn't want to do that by hand. All right. I think even 10 values is a lot to do by hand. Once you get comfortable with Excel, then it's relatively easy to recreate this calculation in Excel, and I'll make you do that. But there's also a variance function in Excel. So you just say, hey, give me the variance of this thing, and it just does it all. Right? But you can do these kind of manual calculations, of course. Right? Once you've found all these squared deviations, right? These are all the squared deviations. Or I should say the sum of the squared deviations. Then we divide by n minus 1. We're told that the answer ends up being 4.11 hours squared. Now, this is the problem with using the variance and why we avoid it in this course. I don't want to deal with units squared because that's hard to imagine. And so here, notice the units of the variance are squared, which is the reason we use the standard deviation in our calculations in this course. Okay? Because if we take the square root of s squared, I get s, but I also get to take the square root of, well, 4.11 and the hours squared. So then I'm back down to hours. Yeah? And so notice the units of the variance are squared, but taking the square root gives the standard deviation. Which we will use in this course. Which is kind of confusing because later on in stats, in upper level stats, you only use the variance. But we start here because we don't want to deal with hours squared, for example. All our units would be squared. Ugh. So this is basically all we'll see of the variance. But it does introduce the calculation a little bit nicer because we don't have that big square root. Okay. But let's talk about why we use the squared deviation. So here, your deviation, remember, is xi minus x bar. And if you don't like the I, it's okay. You can just ignore it. I just wouldn't be proper if I didn't put it on there. No? It's just a generic, any observation, xi. So that's the deviation, right? Any observation, how far is it from the mean? And then the squared deviation is that square. We've talked about the first benefit of squaring these values, right, is to get rid of negatives. Because, right, if you had observations that are equally distant from the mean, which is perfectly reasonable, especially if you have a symmetric distribution, right? Some will be below, some will be above, okay? Then they would just cancel each other out if you just left them as negatives and positives, right? That's a problem. Okay? And so that's one of the problems. But also, what the squaring does is it weighs larger deviations more heavily. Okay? And so if you might remember, and this is just to illustrate, it's not super important. It's all important, I guess. But you might remember y equals x squared looks like this, a parabola. Okay? And so if I plug in x equals 1, 1 squared makes 1. But if I move over 1 unit to x equals 2, all of a sudden, 2 squared is at 4. Right? So even though I've moved from 0 to 1, right, a distance of 1, but then if I move another distance of 1, all of a sudden, because it's further from the mean, say that's at 0 here, all of a sudden that squared deviation is just amplified, right? And the same thing would happen on this other end here. If I have -1 versus -2, they'll map back to, well, I probably didn't line them up very well. So 1 and 4 as well, right? And so moving a distance of 1 from 1 to 2, right, actually moved us a squared deviation from 1 to 4, right? And so it just gets bigger and bigger. Why is that important? Right? Because as values move further from the mean, right? Then we need to take that into account of our spread, right? It needs to reach all that far. And so besides that, you don't need to keep track of this, why it is. But like I said, we will focus on the standard deviation. Now, I guess a little confusing in the beginning. If I'm talking about the words standard deviation, I use the shorthand SD, okay? Whereas in our formulas, we just use a lowercase s. And so that can take some getting used to, but if it's in a math formula, it's just easier if you only have one letter. So as we've already seen, the standard deviation is the square root of the variance. So if we're kind of, I was going to say comfortable with the variance. We've seen the variance, maybe not comfortable yet, that's okay, right? But we've seen it, and so then taking the square root of it is not that bad, right? Because if you have S, which we know is your standard deviation, and S squared is the variance, right? If you have your variance, you can take the square root of it and get back to S, right? Same thing, if you have your standard deviation, you can square it and get back to the variance, right? So you can move between the two. So now, a couple of things. Using that variance that we found earlier, right? We found a variance of 4.11 hours squared. Okay? But now if I take the square root of it, I do have to take the square root of 4.11 and I get 2.03. But now I'm just back to hours, right? Hours squared, square rooted brings us back to hours. And so notice the units are no longer squared. It's important because it's really hard for our brains to think about units squared, right? It's kind of like a space, especially things like hours squared. Not sure I could wrap my head around it. So roughly 2. And so this is a little bit of foreshadowing, I guess. But if we're here, we're family. Is that Olive Garden? When you're here, your family? Nice. Got this bad habit of thinking of commercial tidbits, like old school commercials though, so don't really make sense. But here's a little bit of foreshadowing. So all the data tend to be within 3 standard deviations of the mean. So we can try that. We can go, let's say roughly, I'm not going to, well, my calculator is ready, but let's say roughly 6.71 minus 2 puts me somewhere here. Minus another 2, somewhere here. Minus another 2, I think there. 2.03. You can do it properly if you want to. But you can't get negative slate, so, or can you? Let's say here, here, and here. So you can move out usually 3 standard deviations, and then you'll have covered all the data points, typically. Okay. If you're in business, you might have heard of 6 Sigma. Okay. It's like a strategy, but it's talking about there's 6 standard deviations that you can move. Okay. Which brings me to my next, now I'm going to add a page and I'm going to write a lot. I'm going to write so much. Which brings me to, we have a statistic and a parameter. We did introduce those, but it was at the very end of class, so I understand if you don't remember, but we will always have a statistic and a corresponding parameter. Do you remember what they are? A statistic is a measurement from the sample. Yeah? And so it's a measurement from the sample. Notice the S and the S. That's convenient, right? You can tie those together. Whereas a parameter is going to be the population equivalent, right? It's technically a measurement from the population. From the, and maybe I'll just give myself a little bit more room here. Population. And again, pretty convenient because the P's and the P's link together, right? Parameter is from the population. For each of these, though, if you've calculated, or if you've collected a sample, right, then we can calculate the mean. So far, we've seen the mean. You can calculate the variance. And you can calculate the standard deviation. And this, I didn't write very nicely, but let's do that. I don't need a ton of space for the rest of them. So of course, we can calculate the mean of the sample, right? But remember that our goal is to learn about what the population mean might be, right? And so of course, is there a word I wrote weird, or is it deeper than that? No. Okay. Usually it's about a word I wrote very weird. But, right, and so we want to use our sample mean, but the ultimate goal is to learn about the population mean. And so we saw last day that, okay, a sample mean is denoted by X bar, whereas a population mean is denoted by a Greek letter mu. And it's just mu. The variance, when we've calculated it, it's from the sample, right? So any calculation that we do is a sample calculation, right? And so then what we have is we saw our notation was a lowercase s for the variance. Whereas for the parameter or the population, right, our variance is denoted by a lowercase sigma, which is just kind of an O with a tail on it, squared. So this is sigma squared. And then we know already that if we're working with sample information and we're calculating the standard deviation, we denote it by a lowercase s. Whereas, surprise, surprise, we just use a sigma, right? We just take the square root of it and we end up with sigma, a lowercase sigma. Which represents the standard deviation of the population, yeah, which is where that 6 sigma comes from. If you've heard of 6 sigma. I think it's like a lean strategy or something. I don't know, it's business. Those guys. It is, right? Yeah. Everything operating and yeah, parameters. Yeah. It was really popular and it might still be.
It's like I'm in 3rd year and I just started hearing about it.
Yeah, I know it was really popular like 10 years ago, but that's also when I was in industry. So maybe it's just, I left industry and then, yeah, rebrand. Yeah. But here we focus on stats. So this jump between a statistic and a parameter takes some getting used to, right? And it is really confusing. I'll give you that. Okay? But as long as you keep track of these values are from the sample, right? Things we've calculated, they don't get Greek letters. Greek letters are reserved for the population, which we're trying to learn about, right? If you kind of take a step back and think, okay, well, if I knew what the population was, why would I, if I knew everything about the population, why would I bother sampling, right? Then I don't need to take a sample. I can just look at my population, right? And so that doesn't happen. And so here, these, we use Greek letters. We use Greek letters. I feel like it should be capital. Sold for the population or for parameters. Start weaning you off of it, right? When I say parameters, by definition, right, that's a measurement from the population, so it implies the population. Huh? So for us, these are values that we calculate. Let's do an example of the standard deviation, especially using our formula sheet. I'll go back here. This is the version of the variance that we introduced. This formula, and maybe I'll just grab a clean one actually. Copy. Pasta. What does this version of the formula do? It's just a different way. And depending on what information you have, right, it might be an easier way of calculating the variance. Okay. But let's just briefly talk about how it works, and then I'll abandon ship. How about? So this one we used in the example, used in the variance example. And like I said, my goal is not to make you calculate these things by hand. That's crazy. Most calculators, if you just give it the list of numbers, will just calculate it for you, right? That's not important to me, right? what is important to me is you should be able to look at something like this and pick it apart and understand how you would calculate it, right? That's the value that I'm hoping for you to have. Okay? And so here, s squared is the sum of the xi squared minus n times x bar squared all over n minus 1. I'll use different colors to show you where to start. Well, first place you'll start is you need to find the mean. Right? So here, 1, find the mean, x bar. Then working out from the mean, what you can do is you can square it. Right? That's what the next step is. So whenever you're working with these formulas, you want to start at the innermost thing that you can get to, right? So x bar in this case. And then you want to balloon out. And so then, I don't want to use up all my good colors right away, but they're right there. Square the mean. Right, so now you're at x bar squared. Notice the square is not on the n. Okay. So then multiply that. And now kind of parking lot that value, right? That'll just be a number. Okay. If the mean is 4 and your sample size is 9, right? You would just get 4 squared times 9, right? It's just going to be a number. Okay. So now just kind of, I like to parking lot it, just put it to the side or whatever. And no, I don't need to say that. Okay. Then this one's probably the pickiest part. 4. You're going to square each observation. Okay. So what this is saying, xi squared, and then add those all up. Square each observation, add them all up. Add up all those squared deviation or squared observations, I should say. I should do it in 2 colors, shouldn't I? But I'm running out of colors. Square each observation. Then add them all up. That's going to be a number as well. Right? You're just going to get to the sum. Right? So now what we've boiled down to up here is you have a number minus a number. That's not so bad. Had a little bit of work to get there. Right? Yeah. So the I is it's just a placeholder for any observation. So we call them x1, x2, x3. So generically, we just call them xi. And it's just to confuse you, I think. No, it's to be proper, but also it is confusing. So if you don't like it, you just are comfortable with the x's and you understand that it's each observation, drop the I. Yeah. So now, right, we have a number minus a number. Yeah. Oh, yeah. I don't want to do an example of this one. I want to do an example of this one. We can do a little shorty example. How about that? So we're going to square each observation and then add them all up. Then step 5 doesn't really need a circle, but there. Find the number from 4 minus the number from 3. And then finally, divide by n minus 1. What color haven't I used? Red? No, can't use red. Purple. It's a little close for comfort, but we had to go there. 6 divide 5 by n minus 1. But you'll have to come up with some numbers. Me, because I'm terrible at making up numbers. I usually start with 3 for some reason. And then I'm stuck on odds. But I'll do 3, 5, 9, and 2, just to show that they don't have to be in order.
Are we gonna use those kind of formula?
No, we're just stretching our math abilities. You will have to do it on an assignment, like I said. So you will have to do it, but not on a test, which is really, I know, all you care about. I have to do this on a test? No. But I do need you to be able to look at formulas and understand what they're doing. So that's what we're doing, really. So here's our data set. And now this means that I have 4 observations, and so my n must be 4. I have 4 things in there, just itty bitty. First thing I need to do is find the mean. I can do that. X bar is, let's see here. And I might have to round, and that's okay. 3 plus 5 plus 9 plus 2. It's 19 divided by 4. Oh, nice. If I get a nice number like 4.75, which I did, then I'm not going to round it, right? If it's only 2 decimal places, you should keep them all. Okay. Whew. That's good. Step 1, done. Step 2, oops. Square the mean. X bar squared is 4.75 squared, which is a little bit bigger now. 22.5625. That's step 2 done. Step 3, multiply by n. So here I found my mean, I squared it, I multiply by n, and I need to find that lighter green. 3 is n times x bar squared, which is 4, right? That's why I made a note of what my n was. 4 times 22.5625. Because I've already squared the x bar previously, which I get times 4. I get a nice and convenient 90.25. So now I can parking lot that for a little bit and focus on squaring each observation and then adding them all up. So what I like to do is, for my step 4, is actually create a column next to here with my x squared. Right? Because each value needs to be squared, and then I need to find the sum of all those. 3 squared is 9. 5 squared is 25. 9 squared is 81. Let me confirm. 2 squared is 4. If I add these all up, 9 plus 25 plus 81 plus 4, I get 119. Add a page. So now, if our s squared is the sum of your xi squared minus n times x bar squared divided by n minus 1, you found that this value can be replaced by 90.25, and you already did all this work, and it can be replaced by 119. Right? And you know what n is? N is just 4. Right? And so what we get is we have 119 minus 90.25 divided by 4 minus 1, which puts me at 119 minus 90.25. Let's simplify that. 28.75 divided by 3. I get 9.583 repeating. Which you can just round to 9.583 safely. That's all right. Now that you have the variance, we could find the standard deviation, right, by just squaring or square rooting the variance. We can find the standard deviation by taking the square root. Which means that the standard deviation is the square root of 9.583 repeating. I'm going to keep all my decimal places and just take the square root. And I get 3.095695937. So now you've seen an example. And if you wanted to, yeah.
Can you scroll back down, please?
Oh, yeah. Here. Yeah.
Do you preferably round at the final?
No, I don't care. As long as you keep about 3 or 4 decimal places, it's usually safe, right? And so, but I don't want you to round. If it's something like 90.25, just keep all those decimal places. If it kind of ends naturally, I would say keep them all, right? And one of the main things, so in the homework platform that you're using, I would say the number one thing is just, if it's not accepting your answer, try more decimal places. It's usually just happy if you just give it more decimal places. I would guess that about 50% of the messages that I get about the homework questions, the answer is just, well, I'll just try more decimal places. Because I've looked and I can see that you're doing it right and you're just not trying enough decimal places. All right, so just always give it more decimal places and usually it's happy, right? If not, then but you can still contact me. Right. Then maybe something is wrong. Right. Okay. How about, well, do you want to use these numbers again so we can check our work? So we get the same answer with a different formula? Or do you want new numbers? It's hard to make up numbers. Let's just keep these guys. We actually already did this one. All right. If you ignore the square root, it is just the formula that we just did, right? The sum of the xi squared minus n times x bar squared divided by n minus 1. And then we took it a step further and took the square root, right? So we've done this one already, but I'll attach it here. So you can see it. So the only one we haven't done is this last one. So example, find the standard deviation using, paste that there. S is equal to this. Sorry, that green came from before, but just ignore that. Okay. We've talked about breaking down this formula, but let's do it like we did the previous one, right? Kind of build it out in steps. What was our example data? X 3592. Just because we got some nice numbers and we can confirm that we get the same answer. That's nice. Because we already know what the answer is. Well, it should be this. 3.09569, blah, 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 blah. So where do you start breaking down this formula here? I'm going to latch on to the x bar again. Right. So my first thing is calculate the mean. We already did that, right? So that's nice. Then from each of the observations, and I'm noticing kind of sloppy, there should be an I on here, but there isn't on your formula sheet. Probably because I flip-flop. You show the I, it's confusing, but now we know what it is, so we should probably have it on there. From each xi, right? So from each observation, subtract the mean. Then square each of those deviations and then add them all up. Now, I would say the best way to set this up is if I move this down just a smidge and I make more columns next to my data set. So step one is still find the mean. And we know from earlier that X bar is 4.75, which we need. Then we're going to pick a color, maybe blue for contrast. Inside the brackets, right? So just moving out. Inside the brackets, we first have to take xi minus x bar. And so what I'm going to do here is xi minus x bar. I'm going to make a new column, just like I did with my x squared. Right? But now I'm going to calculate each deviation separately. And so I'll call this 2, and I'll summarize it down here. 2, calculate each deviation. Xi minus x bar. Which is going to look like 3 minus 4.75, which is 3 minus 4.75, negative 1.75, 5 minus 4.75. I guess I should probably do that one in my head. I get so caught up. How far is 9 from the mean? 9 minus 4.75. Bless you. And how far is 2 from 4.75? Notice that you get positive values if it's above the mean and negative values if it's below the mean, right? And so we need to handle that. Our next step, bless you, is to square each of these values. So here, xi minus x bar squared, which is going to be negative 1.75 squared. Make sure you put brackets around it or ignore the negative, right, in your calculator. Because usually if you just do negative 1.75 squared, it doesn't know to square the negative, right? So then it keeps the negative, but that's wrong. And so make sure you wrap it up in negatives. And let's see here, 1.75, or just drop the negative, I guess that's what I do. I get 3.0625, 0.25 squared, 0.0625, 4.25 squared, 18.0625. Notice that I'm not rounding any of these, and that is mostly to make sure that our answers line up from before. And it's proper. 2.75 squared. Oops. Where did it go? I get 7.5625. So 3 is square each deviation. Four is the moneymaker, so I'll use pink. That's the sum of the deviations squared. So what you want to do down here is add these all up for step 4. Sum the squared deviations. Let's start here. 3.0625 plus 0.0625 plus 18.0625 plus 7.5625. I get 28.75. Anyone else get the same? Feel like I might have slipped on some keys, but on my calculator. No complaints? Well, I guess we're about to find out. So now I can replace this whole mess with 28.75. So now I'm off to the races. I can divide by n minus 1, and then I can take the square root. We'll write them out as steps, but I need another page. What's a color I haven't? Red? No. Purple again? Yes. I don't like using purple so close to pink, but it's okay. So then 5 divide from 4 by n minus 1. So we have 28.75 divided by 4 minus 1. Divide by 3. 9.583 repeating, which I'm really excited about because it means I didn't muck up my calculator work, because this looks familiar. What would this be? This would be your variance, right? Because the only thing left to do is to take the square root. But if you didn't take the square root, then the square would still be on the s, which is the variance, right? And so they're the same. So now finally, do I use a womp color? Dark blue, how about? But I'll make a note here. This is the variance. And then step 6 is take the square root of step 5. So then S is the square root of the sum, of your xi minus x bars squared divided by n minus 1. Plugging values in, nice and slow. We can morph this. We've already done the work, but it's the sum of your xi's minus 4.75 squared divided by 4 minus 1. Not a lot we can do here, S, because this is each value, right? But we did find that that can be replaced by 28.75. And so this becomes 28.75 divided by 3 square rooted. And I get S is the square root of 9.58333, repeating. Take the square root of that. I get S is, well, it's roughly 3.095695937. Continues, of course, but I can't see anymore. And that's usually good enough. Luckily, this feels like the same answer that we found earlier, right? So two different ways of getting there, right? I like this way mostly because it illustrates that it is calculating a spread from the mean, right? But I know a lot of people find that this first way is a little bit easier because you only had to square each of the values. You didn't have to take the deviation and then square it and then add those up. So it's a little bit less work. You're welcome to use whichever one you want, but pretty quickly, you'll just be using Excel to do it anyways, right? So that's okay. And I'll never make you calculate it by hand on the test. That's not important. Reading formulas is important in this course.
Did we memorize these formulas?
No, you'll have the formula sheet. Yeah. So as long as you're able to look at the formula sheet and work with those formulas, that's good.
So like the whole point of this is to like understand what like X, I,
Totally.
Okay.
Yeah, dealing with summations and kind of working from the core and building out how do you read these things, because it's potentially been a while or maybe never since you had to kind of dissect formulas. So I just want to make sure that everyone knows how to read formulas. That's the important part. We're just doing this for fun, I guess. No. There are some profs who think it's really important to calculate the standard deviation by hand. I am not one of them. Now, let's go back. I'm just gonna go back to our kind of summary table from the review. Because now for normal distributions, we know how to calculate the mean. It's relatively easy. We now know how to calculate the standard deviation, and we all have a lot of options for doing that, but just pick one, go with it, or just use Excel, it doesn't matter. So now I want to move into, well, what happens if I have a non-normal distribution? Right? What if I'm talking about money or house prices or, like I said, anything money related tends to be skewed, usually skewed to the right. And so what happens if I have a non-normal distribution? I still need a center and I still need a spread. And so now we're going to talk about how do I calculate the median and how do I calculate the interquartile range / what are these things? So, the median is the value in your data set that splits the data in half, okay? If you've ordered it, it doesn't actually have to be in ascending, you could do descending, but that's confusing. So we usually do it from smallest to largest, okay? It's a natural ordering. So if your data values are 0, 1, 2, 3, 4, then the median would be this 2, right? 2 splits the data in half because I have 2 values below it and 2 values above it. Now, on your formula sheet, there is a formula for it, but I don't like it. It's on here because other people like it. And it gives the location of the median. That's not super useful. If you have n observations, oh, I should bump it up here. N observations, then it'll be at the n+1 divided by 2th location. Okay, so if I have 1, 2, 3, 4, 5 observations, it'll be in the 5 plus 1, which is 6, divided by 2, which is 3, the 3rd location. I prefer to use my patent pending, although I haven't submitted a patent, so just pending, I guess, boop, boop, boop method. And so what I do, instead of finding where is the location of the median and then actually going to find the value, what I do is sort the data from smallest to largest. And then you try not to go cross-eyed, because then what you'll do is you'll place your fingers, and let me bring it down so I don't have to jump so high. You place your fingers on the outside, and then you boop, boop. Just boop your way in, and then you find it. I find that that's a lot easier, and it's cute to think about. So 1, sort data from smallest to largest. 2, use the boop, boop, boop method. Use the boop, boop. Has to be 3 boops. Boop method to find the central value. Sometimes you land on a value, then that will be your median. Okay? But if there are an even number of observations, then the median is the average of the 2 values in the middle. Kind of confusing to incorporate the average when we're talking about the median, which we know is different from the average, right? But we just take the average of those 2 values. Okay. So if we have a slightly bigger data set here, 0, 1, 2, 3, 4, 5, right? If I had to find the median, you find the location is at 2.5, not very helpful. Or boop, boop, you land on 2 and 3, so you take the average of the 2. So usually how I denote this is by drawing a circle around these 2 and then a bar down the center to indicate that the median is actually at this bar. It's neither of these values, okay? It is at this bar, and so the median is 2 plus 3 divided by 2, which is 2.5, which is kind of confusing because those are also the values. I'll finish this slide and then we'll do an example with slightly bigger data sets because these are too small. The median is the midpoint of the data. So you have 50% of the values below it and 50% of the values above it. And so it's also what we call the 50th percentile. Okay? And to introduce percentiles, we can say the kth percentile, which is just a placeholder, 90th percentile, 10th percentile, right? Those are all terms that we've probably heard in life, right? Oh yeah, I scored in the 95th percentile. That's really good. What does that mean? means that 95% of the scores were below yours, right? Also, then we know that 5% were above yours, right? But so the percentile just talks about how much data is below it. Kth percentile has k% of data below it. Okay. Example. Find the median of the data. And the data is this. 21, 34, 27, 32. 1, 2, 3, 4. Let's do 3 more. 29. I told you I'm really bad at 34, 37. I'm bad at making up. It's okay. It was not bad. But good catch. So these could be ages. Right? If we went around the room, right? How old are you? 21, 34. I know that's not true, but 27, 32, 29, 34, 37. Right? That can happen. To find the median, first thing you have to do, and it's really important, is you have to sort these from smallest to largest, right? Making sure you don't lose any data points because that's going to make a real mess. Yeah? So step number 1 is sort the data. 21 is the smallest, and what I like to just kind of indicate that I've written it down. Done it too many times where I've lost one. Then I think 27. Then I'm gonna go for 29, 32, 34, 34 again, and 37. Count to make sure that you have the same number as you did before. 1, 2, 3, 4, 5, 6, 7. So our n is 7. Right. And so here, make a note. I have n equals 7. And just make sure you still have 7. 1, 2, 3, 4, 5, 6, 7. Now, this is slightly more interesting data than the 0, 1, 2, 3, 4, 5, right? Because now you could find the location of the median, but you'd still have to kind of count in to get there. And so that's why I like my my boop, boop, boop. And then 2, let's use green. Boop your way to the median, or to boop your way to the center. And so it's confusing because you have to do it simultaneously moving in. Right? And so boop, boop, boop. And I land on 32. So now the median is 32, which means half of my data is below 32 and half of my data is above 32. What if I use the same example? Copy. But I add a data point. So instead of starting at 21, let's add a data point here and have 5, then 21. I'll get rid of these. Those are from earlier. And now my n is 8. First thing I have to do, sort the data. Again, I can kind of cheat because I was lazy and I chose 5, right? And 5 would just go here. And so I can kind of quickly jot them down, sort the data. And we have 5, 21, 27, 29, 32, 34, 34, 37. Make sure I have 8 now, just in case. 1, 2, 3, 4, 5, 6, 7, 8. Good. Now boop my way in. Right. So now boop. And starting here, 1 boop, 2 boops, 3 boops, but I'm stuck on 29 and 32, right? But we know what to do here. We circle them, draw a line through to indicate that the median is actually at this line and it's neither of these values. As a heads up, of course, Excel has a median function, so you can just give it a set of numbers, ask it for the median, and it'll do it. But it does use a fancier weighting technique than just the average. So you might get slightly different values, that's all. Okay, but just as a heads up. And on the test, and I will make you find the median on the test, also because it's fun and we need it for stuff we do later. I want you to use this method. You can find the location and then calculate, but I like boop, boop, boop. So now the median is 29 plus 32 divided by 2. Which is 30.5. Oh. So the median is 30.5. It's not in our data set, but that's okay. I should say boop to find the median. The median and the interquartile range, which we haven't introduced yet, but they're both what we call robust statistics. Okay? And so I'll make a note here. The median and IQR, but just don't worry about that, are robust statistics, which means that they are robust to outliers, right? They can kind of handle outliers better than the mean and the standard deviation, right? Are robust statistics, which means they can handle outliers better than than the mean and standard deviation. As an example, let's use this data set here. And try to erase my boops. Hey, nice. All right. So consider the mean of this data set. We can calculate it, yeah. Handle outliers. And then it says better, which is not clear either. Better than the mean and standard deviation. So if we consider the mean of 5, 21, 27, 29, 32, 34, 34, 37, we can do that, right? Bless you. Now, we're not going to. What happens if I make, instead of 37, I replace this with 370? That would blow up my mean, right? My sum in the numerator would be huge all of a sudden. I'm still dividing by the same number of values. And so the mean would be pulled in the direction of this outlier. Clearly 370 is an outlier, right? And maybe I'll indicate that I replace this whole thing with 370 instead. Right? So that's what we mean. The mean and therefore the standard deviation, which uses the mean in its calculation, they're all pulled towards the outliers, right? And so they're swayed by these outliers. Right? Whereas if you look at finding the median of this set of numbers versus this set of numbers, you would find the same median, right? The median would still be the average between 29 and 32. Median is still 30.5. Because it doesn't care if it's 370 or 37, it just used it as a starting point, right? Boop, 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 boop. And so that's what we mean by robust statistics is, well, it can handle outliers better, which is good. And that's why we use it for non-normal data, right? So if you have a skewed distribution which has outliers, right, then we need to use the median as our measure of center, because otherwise the mean is pulled in the direction of the outlier or the tail. The mean would be pulled towards the outlier. So just the reasoning behind using the median versus the mean, right, for non-normal data. Okay. We've talked about IQR, the interquartile range, briefly, and here it is. We're gonna have Q1, Q3, and the interquartile range. I'll spell it out here. Interquartile range. If we know what the quartiles are, and you can probably get there, right? Instead of the median, which splits your data in half, what if you go a little bit further, slice some more, slice it into quarters? Sure, then you have quartiles, right? So let's start there. The 25th percentile is also called the first quartile, which we write just Q1. Okay? So it has 25% of the data below it and 75% of the data above it. Okay? The 50th percentile we've already seen because it's the median. If you wanted to, you could call it Q2. There's nothing wrong with that. I just like the putting a name on it if we have it, which is the median, right? But it is Q2, right? The second quarter, right? Or 2/4 of the data below it. 2/4 is half, right? And then, which means you have half above it, right? The 75th percentile is your Q3. So it's your third quartile. Knowing the quartiles, specifically the first quartile and the third quartile, and then breaking down the name, inter means between, right? And then quartile and then the range is the distance, right? So it's really the distance between the quartiles, which gets us to between Q1 and Q3 is the middle 50% of the data. The range that these data span is called the interquartile range or the IQR. Now this is on your formula sheet along with some stuff we haven't introduced yet, but I'll bring it in. Yet. It's coming soon. I'll just kind of ignore for now. For another couple of slides, it's not going to be that long. So the interquartile range is on your formula sheet, but it does require you to know what Q3 and Q1 are and how to find them. So how do we do that? Let's see here. We have two examples. Right. An example where we have a sample size of 7, right? And then the example with a sample size of 8. Because they behave differently, I want to work with both of them. Yeah? And so from before, let's start with this. From the first example earlier, we can continue and find the quartiles. So I'll paste that in here. So you've sorted your data from smallest to largest, you've found your median, then you find your quartiles. I'll remove these boops because we'll have new boops now. If you want to split something into quarters, usually you take a roll of dough, for example. If you want to split it into quarters, what do? You split it in half. And then you can line those up and you can split them in half again. Right? And so that's the method that we will use here. What am I doing? Time flies when you're having fun, but we can do the quartiles. We can do it. So from the median, this we already used 32 as our median. And so now my boop is going to start at 29 and 21. Which means that my Q1 is 27. So in this case, Notice we used 32 as the median. So we don't use it to find the quartiles. To find the quartiles. It's just a cutting point. Same thing for our Q3. It's 34. I feel I'm out of time. I'll introduce the next one, but we'll start there next day. Copy. The difference between the first one and the second one is that now this line is the median. So you would start at 29 to boop. And then boop. And then you would take the average of 21 and 27. Right? Slightly different method, depending on if you use the number as the median or if the line is the median. Okay. See you Thursday. Sorry. Got a lot to say.